So how do we generate the radiation beam that treats our patients? Let us start our next lesson with a bit of physics. The accelerating waveguide is located in the gantry parallel to the gantry axis of rotation. A beam transport system is used to transport the electron beam from the accelerating waveguide to the X-ray target. As you can see from this animation, the critical part of this process is generating a radiation beam for treatment. Please think about it in the following manner. If something is moving with a tremendous amount of energy behind it and stops instantaneously, what happens? The energy has to go somewhere. And an example of this is brakes on a car. The brakes on a car get what? Well, they get hot. Why do they get hot? The brakes heat up as the kinetic energy from the vehicle is transferred into a thermal energy. And the electrons originate in the electron gun and accelerate through the waveguide to that desired kinetic energy. The electrons are brought through the beam transport system into the LINAC treatment head, and the reaction is that picture that I just put up there. Here it is occurring in that LINAC head. Okay, the clinical X-ray beams are being produced in the LINAC treatment head upon hitting that target. And that target in our case is made of tungsten. In the end, a fast-moving electron hits a metal, and the energy is transferred into X-ray radiation, or as we like to call it, photons. Okay. Irrespective of the accelerator type, two conditions must exist for particle acceleration. The first, the particle to be accelerated must be charged. The second, the electric field must be provided in the direction of particle acceleration. So what is this telling us? It's telling us that charged particles are attracted and repelled by electromagnetic fields. And we use this for both accelerating the beam and bending the beam. The charged particles will accelerate in the direction of the attraction of the field. For accelerating, we do this in a linear way. Remember the linear way? LINAC, linear, LINAC, linear. I try. They're very similar, right? That's where the name came from. The path followed by the moving charged particles, such as our high energy electron beam, which is used in LINACs, will bend as they cross a magnetic field. The radius of that bend can be accurately controlled by the strength of the magnetic field and depends on that energy of the charged particles as stated above. Electron acceleration employs a source of microwaves that act as a carrier that propels those electrons down that waveguide. And Varian uses two systems. We use a radio frequency generator that creates input microwave, and we're back to a klystron that amplifies that input wave to a usable power range. Okay, now we're getting to the exciting part. So let's review all the components that generate the radiation beam and each one's function. The LINAC injection system is the source of the electrons, and that is known as the electron gun. There are two types of electron guns that are in use in LINACs today. One's a diode gun, one's a triode gun. We at Varian utilize the triode gun because of its instantaneous capabilities of turning the beam on and off, especially for those advanced capabilities like IMRT and gating capabilities, which you will learn more about later on. In a LINAC, the electrons are accelerating following straight trajectories, linear, in nature, in a unique evacuated structure. And what is that structure called? The accelerating waveguide. Okay, now previously we discussed low energy X-rays, and then we also discussed high energy X-rays, and we also discussed electrons themselves. But how do we control these energies? Well, if you want higher X-rays, higher energy X-rays, we need to hit that target, and here it goes, with faster electrons, which helps us better understand the role of the accelerating waveguide. So let's look at a side profile to provide you another view into all these components. The electrons originate in the electron gun, and are accelerated in the accelerating waveguide to the desired kinetic energy that we want. They are then brought through the beam transport system into the LINAC treatment head, where clinical X-ray beams are produced in the LINAC treatment head upon hitting that tungsten target. Look at there. Okay, so what is next? We covered the electron gun, we covered the accelerating waveguide, we've covered the target. So what is that big blue item at the end of the waveguide? Remember when we spoke about the beam transport system? We're not complete yet. The accelerating waveguide is too long to mount vertically, so it's horizontally mounted, as seen from the pictures. We have a problem with a horizontally mounted beam because we need a vertical beam. So how do we solve this problem? The solution is a bending magnet. The bending magnet deflects the beam in a 270-degree loop. The lower energy electrons are deflected through a smaller radius loop, and the higher energy electrons are deflected through a larger radius loop. Now that we have that high energy electron beam in the orientation that we need them, what's next? Okay, so we understand how to create a useful clinical X-ray beam for treatment. Also, we understand that in order to achieve that, we have to hit a target, a metal target. In our case, again, it's tungsten. So, before we reach those flattening filters, which is the next piece that you see here on our screen, and before we reach that foil carousel, we have to decide what energy we do want to treat with. Do we want to treat with photons or do we want to treat with electrons? So as a therapist, I have to select the treatment mode at the LINAC control console. So let's start with photons. Okay, high energy X-rays are forward peaked, meaning that the maximum intensity is located centrally with decreased intensity at the periphery, as you can see here. After we hit the tungsten target and have this forward peaked beam, how do we flatten it out so that we can treat more surface area more evenly? Well, the answer is through using flattening filters, as illustrated above. The flattening filter is a thicker material in the center, and then it thins itself out towards the edges of it. And that provides us a flattened X-ray beam that we can treat with. Now, the irony here is that there are certain treatments in which we want a flattening filter-free beam, right? For its pure characteristics of maximum intensity located centrally with that decreased intensity at the periphery, okay? The beam profile is advantageous when you have that maximum intensity centrally located with that kind of fading away at the periphery for stereotactic work due to its increased energy profile, which speeds up treatments. So now we want electrons. We already have an electron beam. So do we need a target? No. The tungsten target is moved out of the beam line and bypasses it and collides directly what we call a scattering foil. But why do we need a scattering foil? Well, the reason why is the electron beam is very narrow, like a pencil, and with a very small diameter. So in order for us to use it, we need to spread it out to be clinically valuable to us. So a dual foil layer is shaped similar, again, to the flattening filters to achieve an even distribution of electron beams for treatment. We are in the final stage of beam generation. The radio frequency generator system produces microwave radiation used in the accelerating waveguide to accelerate the electrons to the desired kinetic energy. Our power sources is either going to be a magnetron or a klystron. In our case here, for the TrueBeam, it's a klystron, and it is positioned in the gantry stand. In a standing waveguide accelerating structure, the microwaves enter on the gun side and propagate towards the high energy end of the waveguide. The microwave power produced by the magnetron and the klystron is carried to the accelerating waveguide through rectangular uniform waveguides, usually pressurized with a gas. Between the RF generator and the accelerating waveguide is a circular isolator that transmits the RF power in the RF generator to the accelerating waveguide, but does not transmit the microwaves in the opposite direction. Always remember the term linear. Let's summarize everything that we just learned about beam generation. The electrons originate in the electron gun, and in our case, the triode gun. The electrons are accelerated in the accelerating waveguide by the radio frequency power generation system called the klystron. The klystron produces the microwave radiation used in the accelerating waveguide to accelerate the electrons to the desired kinetic energy. Something we didn't talk about before, though, is the variable energy switch, which is aligned with the accelerator structure and allows us to treat a variety of energies. We can treat up to 5 flat field photon energies, 2 filter-free energies, and 8 electron energies on a single platform, and that applies to our TrueBeam family of products. Next, once we get down that waveguide, Varian's bending magnet is next. And the bend magnet also features what we call plus or minus 3% energy slits, ensuring that the beam stability is there. Energy slits filter the electron beam to a tighter, more specified energy bandwidth. The tighter the energy bandwidth, the more stable the beam. When we near the end of the beam transport system into the LINAC treatment head, where the clinical X-ray beams are being produced upon hitting our tungsten target, afterward, the new X-ray photon beam goes through that primary collimator. The clinical electron beams bypass that target because they don't hit the target because it's going to remain pure electrons. And they go to their primary collimator, they go through it, and they hit the scattering foil. The final component before hitting that secondary collimator, which we'll talk about later, and the MLCs, which we'll talk about later, is the ion chamber. And the ion chamber is not pictured here, but it mounts, but it monitors the X-ray dose exiting the machine for several purposes that we will go through again in a later chapter. So now you are versed in beam generation.